Today we're going to talk about a couple of simple but pretty important examples of differential equations. The first one is exponential growth and decay. This is where your differential equation is of the form dp dt is equal to k times p, where k is some constant. The k in this case is sometimes referred to as the relative growth rate, or it could be possible for k to be negative, in which case it would be called the relative decay rate. So for example, if we had the equation dp dt is equal to 0.03 times p, then 0.03 is your k, and so that would be your relative growth rate. But you would typically express it as a percentage, so the relative growth rate in this case would be 3%. And it's worth comparing the relative growth rate to the absolute growth rate, which is just dp dt, the rate of change of p. In this scenario, the relative growth rate is constant. It's just 3% in this example, whereas the absolute growth rate can change, and it depends on the size of p, because it's actually equal to 0.03 times p. So if p is bigger, you'll have more growth, and if p is smaller, you'll have less growth. So this sort of differential equation is a useful model in a lot of real-world situations, such as continuously compounded interest. In fact, in the example I gave you, that would be a good model for a bank account that's earning 3% interest. You'll notice that no matter how much money is in the account, the interest rate is always the same, 3%. But if you have more money in the account, you'll earn more dollars per year of interest than if you have less money in the account. So that's the comparison of the relative growth rate versus the absolute growth rate. So another application is radioactive decay. So this is a case where the K would be negative. And the way this works is that if you have some radioactive material, it actually decays over time, and the rate at which it decays follows this exponential model. So obviously this is important if you're doing nuclear physics, but there's an application that all of us would have encountered at some point in our lives, and that's that they use this model to do carbon-14 dating. When they date how old like a fossil is, they look at how much carbon-14 there is inside of the fossil, because that is a radioactive particle. And they compare that with how much carbon-14 there would have been when the dinosaur died. And then they use the exponential decay model to figure out how much time has passed. Another application is population growth, at least in the early stages of population growth, where there aren't many constraints in terms of the resources that are available. You'll typically see populations grow at an exponential rate, because each animal would have a certain number of children, and then those children would have a certain number of children, and as long as that number is approximately constant, then the growth would look like exponential growth. Now, if there are constraints, like suppose that there is some maximal amount of population that the environment will support, then there would be a different model that you'll use, and we'll talk about that model later. And another example that's very relevant for us right now is virus spread. If P is the number of people who have the virus right now, and then you assume that those people are going to spread the virus to other people, and then those people are going to spread the virus to other people, and if that rate of spread is approximately constant, then it will follow this exponential growth model. And in fact, you may have seen articles that refer to this number R as representing the rate of growth of the virus. That is actually related to the K in the model by this formula that R is 1 plus K. So if R is greater than 1, that means that K is positive and the number of people who have the virus is growing. Whereas if R is less than 1, then K is negative, and that means that the number of people who have the virus is decaying. And of course, this number isn't constant. It depends on what we're doing as a society, how much social distancing we're doing, how much we're doing in terms of wearing masks and stuff like that. And that's why you actually see the numbers going up and down. But over short periods of time where people's behavior isn't changing that much, the exponential model follows the data pretty well. And then finally, I will point out that there are more sophisticated models of virus spread. This is really the most basic example. There are more sophisticated ones that involve different groups of populations. There are people who are immune, there are people who haven't gotten it yet and are susceptible, and there are people who have it, and then the people who have it will eventually either die or be cured, and then they'll move into the immune column. But those are more complicated. Those are like systems of differential equations where you have lots of different variables that are interacting with each other, and you would study that in a more advanced class. So anyway, let's get back to the math. If we look at this differential equation, we can try to plot what the slope field looks like. When p is equal to 0, then dp dt is going to be equal to 0, and so those slopes will always be horizontal. And then, if k is positive, we would start to see positive slopes when p is positive, and the slopes would become larger and larger as p becomes larger and larger. And then, even though it usually isn't relevant in these real-world applications, you could have the possibility that p is negative, in which case the slopes are negative. Actually, that's wrong. In the case of continuously compounded interest, you could have a situation where you're in debt, in which case the interest accumulates and makes you more and more in debt. And that would be a relevant situation for this p being negative. And so from the slope field, you can see what the solution curves look like approximately. And you can sort of tell from this, or at least you'd be willing to believe me if I told you, that the solution curves are exponential curves, where p of t is a constant times e to the k times t. You'll be solving for this in the worksheets, so I'm not going to do the solving right here. But that's what the solution curves end up looking like. So another important example of a differential equation is what's known as Newton's law of cooling. So the equation for Newton's law of cooling is dH dt is equal to minus k times h minus a, where k and a are both constants. So just like with exponential growth and decay, there are actually a lot of different applications of this equation. But the main application that we would have in mind would be something where, say I have a hot cup of coffee, and then over time the temperature of the coffee cools to room temperature. What is the formula that describes the temperature as a function of time? So in this context, A would represent the ambient temperature, as in the temperature of the room. And this K doesn't have a simple interpretation. It's actually a catch-all for a lot of different things, which basically affect how quickly something will cool. So different substances will cool at different amounts. They might be insulated by different amounts. The shape of the coffee cup can actually affect how much it cools. So there are lots of different things that go into the K. And in practice, you actually have to do experiments to measure what the K is, because you can't just calculate it based on first principles. So anyway, let's look at what the slope field for this differential equation looks like. So when h is equal to a, you'll get 0 on the right-hand side, so you'll have dH dt is equal to 0. And so you'll have horizontal slopes there. And then when h is positive, you'll have h minus a being positive, but being multiplied by a negative k. I should point out that the k is always going to be positive in this sort of application. So for those values of h, you would have negative slopes, and they would become more negative as h grows because h minus a would become bigger and bigger. And so from the slope field, you can get an idea of what the solution curves look like. They sort of asymptotically approach a. So that means that if something is very hot, it's going to cool quickly, but as it gets closer and closer to room temperature, then the rate of cooling will become slower and slower, and the temperature will asymptotically approach room temperature. Now we can also consider what happens when h is less than a. In that case, h minus a will be negative, and you're multiplying by minus k, and so that would make a positive dH dt. And if the object is just a little bit less than room temperature, then the h minus a is small, and so the dH dt will be small. But if the object is much, much less than room temperature, then h minus a will be large, and you'll have a very large dH dt. And so you have solution curves that look like this. And what that means is that the exact same equation, even though they call it Newton's law of cooling, it works equally well for heating. And then finally, I'll point out that there's an interesting feature that you see in Newton's law of cooling, which is the existence of an equilibrium solution, which is where the temperature is constant. In this case, the equilibrium solution is when h is equal to a. You can see it in the slope field, and it also makes sense intuitively. If something is already at room temperature, then it's going to stay at room temperature. But also, you can see it in the equation, because if you plug in h of t equals a into the equation, then dH dt is equal to 0, and the right-hand side of the equation is also equal to 0, because h minus a is equal to 0 if h is equal to a. And so the equation works. And this is something that you can do more generally, not just with this differential equation, but with any differential equation. You can look for equilibrium solutions by plugging in a solution where the equation is constant, and then the derivative will be equal to 0. And when you do that, you'll end up with an equation where you can try to solve for that constant, and those solutions would be equilibrium solutions. So actually, now we can go back to the exponential growth decay model, and we can see that that also has an equilibrium solution. So remember that the equation was dp dt is equal to k times p. So to use the equation to find the equilibrium solution, we would plug p equals c and dp dt equals 0 into the equation. And so when we do that, we get 0 is equal to k times c, and the result is that c has to be equal to 0. Note that I'm assuming that k is not equal to 0, because if it were, then this would be kind of a trivial equation to begin with. It would be where there isn't any growth or decay happening. And so the conclusion is that p equals 0 is an equilibrium solution. And again, you can see this equilibrium solution in the slope field, where you have a constant solution where p is equal to 0. And then, of course, this makes sense intuitively. Like if you don't have any money in your bank account, it doesn't matter what the interest rate is. It's always going to stay $0. All right, so one more thing. If you compare this equilibrium with the one that we saw with the Newton's law of cooling, you'll notice that there's an interesting difference in the behavior. With Newton's law of cooling, you had a situation where things would approach the equilibrium over time. The temperature of an object would either cool or heat so that it would approach room temperature. With exponential growth or decay, you have a situation where solutions move away from the equilibrium over time. If you have a positive population or a positive amount of money in your bank account, then that will continue to grow and move farther and farther away from 0. And so there's terminology to distinguish those different sorts of behavior. You would say that an equilibrium is stable if solutions move toward it. And you'd say that an equilibrium is unstable if solutions move away from it. So with exponential growth and decay, the equilibrium solution is unstable, whereas with Newton's law of cooling, the equilibrium solution is stable. There is another possibility, what's called semi-stable, which is where the solutions move toward it from one direction, but move away from it in the other direction. We'll see a precise example of this later, but for now I'll just draw a slope field so you can see what the slope field for this sort of thing would look like. So in this slope field, you can see that you have an equilibrium solution, but then for solutions that are above that equilibrium, they would move up. They would, look sort of like an exponential curve. So on that side, the equilibrium is unstable. Whereas below the equilibrium, the solutions tend to approach the equilibrium. So on that side, the equilibrium is stable. So in this case, you would say that the equilibrium is semi-stable. And this sort of analysis that involves finding equilibriums and looking at their qualitative behavior can be really useful because it doesn't involve a lot of detailed calculations. The math is pretty simple, but you can actually get a lot of useful information that might be good enough to describe how a system behaves in a real-world situation. All right, that's it.